Thank you very much. I think you can see my presentation. Indeed, in the next few minutes, I will give you some information about the recent CERN Quantum Technology Initiative. So this talk, of course, is given on behalf of a team of people. We have today a task force at CERN composed of people from the IT department, from the EP department, from theory, so experimental physics, theoretical physics, and the information technology mainly, to understand the potential of quantum technologies in the future for high energy physics specifically, but more in general for science. I have a few slides about CERN, so I don't know if, I expect most of the people attending to be very familiar with CERN, so I will not go into details, but just to remind everybody, how CERN typically works. CERN manages the accelerator, and the accelerator is used as an international facility for collaborations, the experiment, using it as a tool, as an instrument for fundamental physics research. And today, the main accelerator is the LHC accelerator. There are 4 experiments: Atlas, CMS, LHCb, and ALICE, performing different types of observations using the LHC. Now, from a computing point of view, of course, this is the starting point, the transition between the actual world and the computing and computer science world. It happens in the detectors. There are at least, very, as a simplification, there are at least 4 main classes of computing workloads that we are looking at from a quantum technology point of view, quantum computing especially. And these classes are the data acquisition part, which is of course the initial collection of data from the sensors of the detectors. Then track reconstruction, where this data is transformed into actual tracks, the traces of the particles generated by the collisions and traversing the detectors, and of course the final data analysis, where the reconstructed information is processed to actually go back and understand what was at the very moment of the collision. And of course there is the big class of simulation that tries to understand what would happen inside these detectors in the accelerator, try to apply the more theoretical aspects of physics to generate something that then can be compared to the experiment, to understand, to prove or disprove theories and understand whether new physics has been found. So this is the standard model. Well, in terms of computing, is the default model working of all the experiments today. And as you know well, it has been until now very successful. The physics standard model has been sort of completed with discovery of the Higgs boson. Now, of course, there is much more than this in the universe. Broadly speaking, the standard model is capable of explaining about 4 to 5% of the universe, and there is a lot more outside there that today is not fully understood. All the questions about dark matter, dark energy, the relation between gravity at the macroscopic level and the quantum mechanics at the microscopic level, and all the issues about why there is no actual antimatter in nature. Although not only theory, but even in practice, antimatter can be produced. So a lot of questions and more are still open. So the work of the experimental physicist and the theoretical physicist and of scientists in general in this field is far from finished. So the CERN and the LHC experimental schedule is still very much at the beginning. Now you have here an initial, a snapshot of the LHC program. Don't look at the dates. The dates are being revised. This is not up to date, and of course the current situation, sanitary situation in the entire world has already had an impact on the schedule. This is being revised. But broadly speaking, of course, for the future, we are looking first at the next evolution of the LHC, the so-called high luminosity LHC, where the luminosity should increase by an order or two of magnitude and allow to explore more in details not only the known physics but also look a bit beyond the known physics. And of course, we are also targeting in terms of technologies and looking into the futures. We are targeting programs beyond the high luminosity LHC, like the future linear accelerators, and the future circular accelerators that are being designed and discussed. So our investigation in quantum computing and quantum technologies in general fits into this context. It's about looking at what technologies are coming up that could support, accelerate the computing aspects of the physics research in the next 5, 10, 15, 20 years. And of course, in this context, we have started looking a bit more in detail into quantum computing, which has seen a very rapid acceleration in the past few years. So already today at CERN, there are a number of unique activities and unique expertise in different fields, and especially in the 4 traditional fields of quantum information science. And these fields are, the areas traditionally are quantum computing, quantum sensing, quantum communications and networks, and the more theoretical aspects of quantum field theory, information processing, and direct quantum simulation. So there are a lot of these things happening already at CERN, but until now, we're not really classified as quantum technologies using more recent terms. So we started a process about a couple of years ago to rationalize a bit these activities and try to understand how to make them a bit more organized across CERN and also to support the high energy physics in more general ways. So 2 years ago, already as a CERN Open Lab, we organized one of the first, I believe, workshops to discuss about quantum computing for high energy physics. This was a very successful workshop. At the end, there were more than 400 people registered. At the time, almost everybody was on site. There was a very lively discussions. There were people from, of course, from the HEP community, from industry, from other sciences, discussing about the state of the art of the technology and the possible applications in physics and in other sciences. So since then, this happened about 2 years ago now. Since then, we have started a number of pilot projects and collaborations to explore a bit more in detail these emerging fields. Now, as a consequence of these initial discussions, we have proposed about a year ago, a bit less than a year ago, we have proposed the CERN management the possibility of creating a quantum technology initiative at CERN. So there are a lot of things, a lot of initiatives, a lot of projects and programs running in Europe, in the CERN member states, in the experiment member states, member institutes, and internationally. So this, of course, is not new. The CERN Quantum Technology Initiative has no claim of being the first in anything. Actually, a lot of things have started already in the past several years. But we thought it was time to understand how CERN and the HEP community that looks at CERN as a reference could invest a bit more effort, a bit more time into these activities and create a broader program of investigation. So this proposal, the initiative, has been approved, and formally speaking, it has been approved in June this year by the Scientific Policy Committee at CERN, and in September by the Council. so all the member states. So the feedback was actually very positive. And now we are ready to start. So it is essentially an R&D program organized across the 4 areas of computing, sensing, and quantum information processing. It will be mainly based on research programs and projects with students, doctoral students, postdoc, visiting scientists, but in a very important way, will be done in close coordination and close collaboration with any initiative happening in the member states, in Europe, and the neighboring countries in general, and also internationally. There will be, for example, an advisory board composed of representatives, experts in quantum technologies across the member states to guide our investigation and align what the CERN Quantum Technology Initiative does with the programs in the different member states. So what has happened until now? So far we have defined a set of high-level objectives for the 4 areas of investigation of computing, sensing, communication, and theory. Again, these are very high-level objectives. So these are our starting points. Now we are organizing a number of brainstorm events and discussions to go more in details in these events and understand what are the priority projects that CERN should support, should take part in, and how to do this in collaboration with the other national and international initiatives. So, for example, you see here a few ideas for computing. Our main objective is to assess the role of quantum machine learning. So of course, we see everywhere a growing use of machine learning, deep learning techniques in all the different computing workloads. For HEP, we would like to understand if there is in the future potentially an advantage in using a quantum approach to these machine learning activities. We want to build the experience in using the tools, the software, the hardware, quantum computing simulators, possibly have access to some hardware, and understand how to increase and to build the skills and the human capacity, the human knowledge of our community around these themes. For sensing, again, there is a lot already going on in, let's say, low energy experiment, more related to quantum, to dark matter searches, antimatter. So those activities will continue, but we will also look at possible applications to high energy physics, new classes, new types of calorimeters, of particle detectors, and understand what is the potential for future HEP detectors. Communication is also a very important class of applications. There are a lot of discussions today in Europe and in other parts of the world to build the next generation of quantum internet applications. So I will give you more information in a moment. And of course, the aspects of theory. And again, also, I will show you a bit more in a moment. So let me start with one important thing, of course, is knowledge sharing, education, and training. So we are talking about technologies that are really emerging, for which the people who can claim being experts on this are not so many at the moment in the world. So we would like to contribute to growing the knowledge and sharing this knowledge across the community. So as part of these activities, we will also organize education and training opportunities at all levels. So quantum computing, quantum technology courses, academic collaboration, but also training on actual technologies in collaboration with industry and other laboratories. So this is a very important part of this initiative. So let me start with quantum computing. So as I said, our main objective in quantum computing is to explore, especially the space of quantum machine learning. And we have started a number of investigations on different types of networks, of deep learning approaches, to explore the different workloads for simulation, classification, reconstruction, and so on. And we are looking also at possible application of true random numbers, random numbers to see whether, for example, using these numbers might give advantages in certain classes of problems, so for seeding, track reconstruction, or for Monte Carlo models, for example. And we are also looking in the future at special application of quantum technologies for classes of problems that are not typical of HEP, but might have a very important impact in terms of science and also on practical applications like encryption, like security. These applications are more typical of medical research, life science, or industrial applications. But as part of CERN OpenLab and as part of our collaborations with industry and multidisciplinary activities, this is also an area that we would like to explore. A few examples in this, so quantum generative models. So you might be aware of the fact that, and we use a lot of, for simulation, we are, of course, big users as a community of Monte Carlo models. And they are, of course, very, very efficient and very precise, but also require a lot of resources. And if you want to scale up Monte Carlo models, you also need to scale up resources, which has an impact in terms of the worldwide infrastructure we are using today. So in the past quite a few years, many people in the community have started looking at alternative models, like generative adversarial networks. It is possible to develop faster approaches to simulation that scale better with resources compared to current models. This has been proven to be possible. It is not production level, but it is very promising, and it is possible to show that at least under simplified conditions, these generative models have the same precision as Monte Carlo models with much better performance and scalability properties. So it is the same for quantum generative models. So we have started looking at this aspect, and with a sort of hybrid approach that puts together in the two parts of the generative and the adversarial networks, combining one quantum network and a classic network as an experiment, as an initial experiment. So we are using a quantum generator and a classic discriminator. And on very simple initial models, one-dimensional, two-dimensional, again, we have seen that these models are actually quite precise. They give the expected energy profile, energy distribution of a particle, in this case of a single particle crossing a simple calorimeter. Now, one problem of today quantum generative adversarial network is that all the implementations we know of are able to sample, are able to embed the energy distribution, but cannot sample individual images, which is what you want with generative adversarial networks. You want to build synthetic but individual images very similar to what you would find in reality. So we have been working with Cambridge Quantum Computing and with IBM to move the state of the art forward. And we are experimenting today, still work in progress, but we have new models that are able to combine the existing technology, existing methods to embed the energy distribution in the quantum circuits with a method to extract individual images from the circuit. Again, this is not far from being production, but it shows promising properties. It converges very quickly. It is quite stable, and in these initial models, it shows quite interesting properties. A second example is track reconstruction. Again, track reconstruction today is done with methods like Kalman filters, for example, to follow the dynamic properties across the different dots and reconstruct the tracks. But already in the past, methods like graph networks have been considered to solve this reconstruction problem. There have been international challenges, for example, like TrackML, which and a couple of Kruggel international challenges to experiment with this model. So again, very promising, and we have started working on a quantum version using an approximation of graph neural networks using 3 tensor networks, a quantum implementation of tensor network. And again, on simple examples, this shows interesting properties, very promising. So you can see from the graph at your right bottom, it's a comparison of the performance of 4 different cases. There are 3 cases, red, blue, and yellow, of classical solution to a simple problem of node identification, with increasing level of hidden layers, 1, 10, and 100. And the green one, the top one, is the quantum tensor network implementation with a single layer. And you can see that just with a single layer, the rapidity in converging to a very, relatively very accurate solution is superior to the other classic approach, even with a much higher number of layers. So again, this is a toy model. There are more sophisticated ways of solving these problems that don't require quantum computing. But comparing apples with apples, comparing the same conditions, the quantum version shows much better knowledge discovery and representational power than the classical counterpart. So worth exploring further. And also, in the third example is for classification. This is work that has been done by Professor Shaolan Wu as part of Atlas and the University of Wisconsin. And we have supported this project as openlab. It's about reproducing one of the channels of the Higgs boson decay. This was in practice one of the discoveries of the Higgs boson a few years ago, in 2012. And the Professor Wu team has reproduced the same case using a quantum support vector machine approach, which again is showing interesting properties. You see from the graph again, right bottom, that the quantum approaches, the red line in this point and the yellow line. The red line is on software simulation, quantum software simulation, and the yellow line is real hardware. They are comparable, at least, with classical method, classic SVM or boosted decision tree approaches for the same type of problem. But again, it has been seen that they converge rapidly, more rapidly, and they require less data than the classical counterpart. So all interesting things that are worth exploring more in the future. And the way we are going to explore this in the future is to contribute, at least to start with, to the creation of a quantum computing simulation platform that in our plans will be composed of both quantum computing simulation, so simulation on classic hardware, but eventually also composed of access to real quantum hardware in collaboration with companies that are producing today quantum hardware. And the platform, the idea is to capitalize on our expertise as a community in creating distributed infrastructures and create something that can be used to give access to a distributed community of researchers to, first of all, to learn how quantum computing works. The idea is to have prepackaged simulators of various types. There are many different simulators from different companies, Qiskit, Cirque, and Penny Lane, and many others. So we would like to give access to scientists and researchers to a pre-configured environments, Jupyter notebooks, code repositories, to let them start their learning curve and their investigations. And then in time, this platform, as it grows and as more and more qubits can be simulated, we will also start deploying more sophisticated experiments and projects on the platform. And the idea is to do this in collaboration with other sites. So if other sites are interested, if you can dedicate some of your infrastructure, typically GPUs, but CPUs are also efficient sometimes in this case, we would be very interested in discussing how to create different national, regional pools of quantum computing simulation facilities and work together in building a larger infrastructure. Now, in terms of sensing, I mentioned the initial investigations are more for low energy physics, antimatter or dark matter searches. There are many ongoing investigations on devices like magnetometers, squids, TESS, transition edge devices, and these are used already to detect, to build devices, very precise, very sensitive devices for measuring properties of particles. The gravitational effects, or direct measurements of mass or charge ratios and spin, direction, electric field, and so on. Now, this will continue, but it is based on something that is quite close to a standard quantum approach. It's measurement of discrete changes of quantum states. Now, can this be applied to high energy physics, where the scenario is completely different? We're not talking anymore about the individual changes of quantum states, but of a continuous process of particle crossing the sensors and in the detector. So again, this is for the future, but we are brainstorming a number of ideas. Is it possible, as a question, to use nanotechnologies, nanodots, nanowires, special quantum mechanics effects to create, to build new classes of detectors, of scintillators, of particle identification devices, of calorimeters that can be efficiently used in this context, which higher sensitivity, lower energy requirements. So there is no definitive answer. Of course, this is an investigation. The idea would be to find a way of priming in some way these detectors, putting them in a special state that then reacts very quickly to the crossing of the particles across the sensors, but giving a much more precise signal. Or, for example, in case of a possible application of nanodots, they would be the effect of a particle crossing a nanodot is emission of photons, and these photons have a particular frequency, color, that depends closely on the size of the cavity inside the nanodot. So by building a controlled arrays of nanodots with different sizes, maybe you can detect very precisely where particles have crossed the detectors by analyzing the scattering, the scintillation, and not by connecting the sensors with wires, which would allow to work really at nanoscales. Is the speed enough? These devices react at the level of tens or hundreds of picoseconds. So it is not far from what is needed in the future, but there is still some work to do. Quantum communication, I mentioned quantum internet. As you know, CERN started the web in some way, but more in general, we have taken part in establishing worldwide international network infrastructures in Europe or internationally. CERN openlab specifically, almost 20 years ago, put in place a network link between CERN and the US, which for some time was the fastest transoceanic network link between Europe and the United States. So we have some history of doing this. So our plan, our objective there is to take part in all the initiatives that are happening today in Europe and elsewhere in the world in establishing this new generation of quantum internet links, but also quantum internet devices. A big issue today is that quantum computing, quantum technologies are not very data friendly. So talking about big data with quantum today doesn't work. But if we can in the future come up with a quantum equivalent of today memory or storage devices, then it would become very, very interesting. And this has to be part of a future quantum infrastructure. So we are very keen in working on these topics. And in terms of, I mentioned our interest in working also on less physics related, more life science or security related activities. So we are discussing with initiatives in Europe, specifically with the OpenQKD project. OpenQKD is a project funded by European Commission to design, investigate the feasibility of deploying pan-European quantum key distribution links for secure data transfer. And we have recently been awarded a small sub-project as part of OpenQKD to investigate how to use a quantum key distribution on a proof of concept of end-to-end data analysis pipeline. So the idea is to start with data at rest, move the data across links, analyze the data, transfer the results back, audit and monitor the transactions, but by securing with QKD all of these links. So to have data encrypted at rest, moving encrypted data on encrypted channels, doing data analysis on encrypted data using techniques, for example, like homomorphic encryptions, and then implementing quantum version of blockchains to complete the picture. Again, it's very speculative. A lot of this cannot be done today. For example, doing really doing data analysis, especially training using deep learning on homomorphically encrypted data today is a big challenge. But this would be one of the first investigations to explore the end-to-end data analytics pipeline in this kind of scenario. And finally, in terms of theory, this is something that it's a frontier for many universities and research labs in the world. So there is work going on at CERN on a number of theoretical aspects, lattice, QCD, simulations, and information processing. A lot of the work done today, especially work to go beyond the standard model and doing dark matter searches type of activities, rely on Monte Carlo, very sophisticated Monte Carlo simulations that require HPC type of infrastructure. Nonetheless, even having all the HPC resources that we can think of, there are problems that per se cannot be solved by classical methodologies. The finite sign problem, the sign problem is one of these type of problems. The special effects in parton showers, real-time transfer phenomenon. These special quantum mechanics classes of problems are hard problems to solve, hard also mathematically, and cannot be easily or not at all solved with Monte Carlo classic approaches. So maybe these are classes of problems where a quantum approach and developing appropriate methodologies and algorithms would allow moving the state of the art and the knowledge forward. Direct quantum simulation of less accessible quantum systems on quantum hardware and extract information directly from this simulation. So there is a lot of work to do, and this program is really at the beginning. We have some ideas. We are looking for more ideas. We are looking for collaboration and for working with a much broader community than just CERN. Of course, we welcome all sorts of input at this point. If anybody has ideas, wants to explore these ideas together, take part in our exploration, or invite us to take part to their exploration at all levels, engineering, computing, sensors, networks, of course, we are absolutely available to discuss about doing this. There is at the moment a placeholder website. As I said, the the formal approval only in September. So we are building this. There is a placeholder website called simply quantum.cern. It's just a web page with links. We are preparing a more interesting website with all information about the activities, the projects, the training opportunities. That this will be available in a few weeks. But in the meantime, please feel free, go to this website, contact me, and I'll be absolutely interested in discussing with everybody. Thank you. Thanks a lot.
Okay. Thank you very much, Alberto. Can you hear us?
Yes, I can.
Oh, okay. So first of all, we have 2 questions in the chat. So maybe can I ask Zoltan Lehotsky to make his first question? Zoltan?
Sorry, I was muted. Yeah, so I would just be interested in what collaboration you possibly have already with Wigner in the field of quantum computing, given that as I see, not just from this event, but also from various EU events, that quantum computing is seems like a very much strategic field in the foreseeable future for the EU.
Yes. So yeah, absolutely. So I mean, I didn't get whether it was a question or a comment, but in any case, yes. I mean, if you have ideas to collaborate, or if you are suggesting ways of collaboration, absolutely yes. So in terms, you mentioned Europe, so we are not directly part today of the quantum flagship or project in the Quantera program, but we are in close connection with them. We are taking part in we are associate members of the quantum project that has been funded by the European Commission to explore quantum computing for HEP, and we are increasing our participation as a CERN in all these activities.
Okay, thank you, Zoltan. So there's another question from Zoltan Cimborás. Cimbi, are you online?
Yes, thanks.
Please make the volume a bit higher.
Yes, thanks a lot. I hope you hear me.
Yes, I do.
So thanks a lot for the really nice talk, and also about these quantum machine learning type of enterprises. By the way, there will be a talk after my talk, which is also concentrating on quantum machine learning by Donny Nagy. My question is that what you skimmed through were always qubit-based quantum machine learning algorithms. Of course, we know that there are those photonic quantum computers built by Xanadu. I mean, you mentioned, for example, PennyLane, and Xanadu is the one that is doing the software PennyLane, which is also good also for qubit-based, let's say, machine learning, and also PsiQuantum. And those are actually somehow a more natural generalization of, say, certain type of continuous neural network models. So are you also planning to look at Q-mode based, so photonic based quantum machine learning algorithms? That's my first question, and then I have another one.
Yeah, very, very quickly, yes. I mean, we are already doing that. I didn't mention this, but especially for the GAN investigations, we are looking at continuous variable approaches. Because as you say, those problems are better suited for photonic approaches rather than qubit-based. We are discussing with both PsiQuant and Xanadu on possible activities. Absolutely. Yes.
Mm-hmm. And my other question is, so it's more based around simulators. So are you trying to develop both hardware and a new type of software, let's say, based on, I don't know, tensor network models for simulators in CERN or something like that? Because we have this quantum initiative here in Hungary, and we are also trying to do some stuff like that, actually.
So yeah, for this I don't have a definitive question. So it might be, at the moment, the answer would be no, because I don't think, very humbly, I don't think that we have enough knowledge and enough resources to really commit to developing new technology, hardware or software. However, it is not excluded. There is technology at CERN that can be used for quantum hardware, traps of various types, so cryogenically cooled electronics. Cryogenics is a big component of the infrastructure. So that is possible. And in terms of classic simulation, we are investigating, for example, some FPGA-based approach of simulations, but these are very, very initial discussions. Again, I cannot tell you in this case, I cannot tell you anything concrete, but I'm certainly interested in discussing more in the future.
Thanks a lot. I'm also interested in discussing this. Thank you very much.
Sure.
Okay, thank you, Cindy. Anybody else from outside or inside further questions? See anybody? Then I would make also just to make a kind of little bit of advertisement like question to you. So if somebody would like to join to these activities at CERN, so should it go bottom up or up bottom? So shall I go to you with a kind of certain problem which I would like to solve and maybe discuss with you, or the other thing that I should find a proper person in the CERN system, for example, if I'm interested in quantum sensors or future detector developments based on these techniques, then I should go directly to the certain point. So which is the most efficient?
So you put me in a difficult position. So let's say that if you know someone at CERN that is working on things you like and you want to talk to them, by all means, absolutely, I'm not telling you that you should not talk to anybody. However, the CERN Quantum Technology Initiative has been created exactly to rationalize a bit all these contacts. So at the moment, I'm the coordinator of this activity. The task force has specific coordinators for quantum computing, sensors, networks, and theory. So at the very least, we can help you understand, unless you have a specific person in mind, if you contact me or one of the coordinators, we can tell you what is the state of the art and who might be interested in what you want to discuss. So both approaches are possible. My suggestion would be to at least let us know that you have this interest, so we can set up some more structured collaboration.
Yeah, good. This is what I told. Just I wanted to let to the others because maybe they are also they not really know the CERN structure as you mentioned. But maybe one further thing that I can imagine that you most likely have regular events where even newcomers can join. Do you have something in the near future?
Meetings for? Sorry, I didn't understand.
Yeah. Something like meetings or which is not super specific, so more general in relation to this quantum initiative, and then join and learn and try to figure out. I mean, this used to be the case when you start something that you don't really know what you want to learn or do. So.
Yeah, correct. So, so we are building that. Let's say we are going into, it's like concentric circles. So there is a task force. It's about 10 people. We are organizing now in November a CERN internal brainstorming meeting to understand who is interested in CERN in working on this, and then the plan is to organize a much broader meeting to create this kind of links. So it will certainly happen, and I'm absolutely interested in understanding the right timing, the right contacts, the right place, the right channels for doing this. And at the same time, we are organizing education events. So this is something, if you have people that are interested in knowing more about the technology, then we will provide free access. This is Zoom, broadcast-based courses on quantum computing. There is one that will start in November for 6 weeks, 2 hours per week, as an introduction to quantum computing that covers the fundamentals, the basic quantum computer programming, a bit of a hands-on exercise. It's really introductory, but this is not to discuss, it's for learning. So what you mentioned is absolutely necessary. We are not there yet. but we need to do it.